Welcome back to the Explainer. Okay, today we are diving right into the deep end. The incredibly high-stakes, absolutely uncompromising world of industrial motor brakes. Specifically, we're going to unpack exactly how dual-coil brake systems work, and we're using SEW Eurodrive setups as our main example today. Because, look, if you're working around industrial machinery, you already know that keeping a massive load safely suspended in midair, yeah, that's not a gentle suggestion. It is an absolute mandate.
So I want you to think about this for a second. What actually happens when 400 volts of raw electricity meets a miswired industrial brake? I mean, we aren't just talking about, a tripped breaker or a blown fuse here. We are talking about immediate, catastrophic failure.
To put it bluntly, the friction desk overheats, smokes, and literally turns to ash within seconds. It's a terrifying thought, right? Especially when you remember we are dealing with systems holding massive, heavy suspended loads. If these brakes get wired up incorrectly, the results aren't just an expensive repair bill, they are incredibly dangerous.
Okay, let's dive into this. We're going to break down exactly how to prevent these disasters step by step. Today we'll cover 1. The fail-safe engineering problem. 2. Dual coil logic explained. 3. Wiring the three-wire system. 4. The catastrophes of miswiring. And 5. Safe testing and diagnostics. Let's get to it.
All right, kicking things off with Section 1, the fail-safe engineering problem, the mechanical challenge.
So, unlike the brakes in your car, industrial motor brakes have this all-or-nothing fail-safe design. They're electrically released and mechanically engaged. That means if a facility loses power, boom, massive internal mechanical springs instantly force an armature plate against a friction desk, fully locking the motor. There is no middle ground, no variable torque, just locked or unlocked. But here's the real engineering puzzle. Pulling a heavy spring off that friction disc against all that tension, that takes a massive amount of magnetic force. But simply holding it open once it's already pulled back, that actually requires very little force at all. Which brings us right to Section 2, dual coil logic explained, the two-stage solution.
This is the brilliant part. This is exactly how dual-coil brake systems actually work. They split the job into two distinct phases. First up, you have the startup phase, or what I like to call the kick. This uses a low-resistance accelerator coil to take the initial surge of current. It creates raw, massive magnetic power to overcome those heavy springs we just talked about. But if that much current stayed on, the coil would literally melt down. So the system immediately switches to the holding phase, or the float. This phase uses a high-resistance coil that drastically chokes back the current, keeping the brakes safely open indefinitely without generating all that excessive heat. And this brilliantly illustrates how that resistance split actually looks. The low-resistance accelerator coil, which is known as the BS coil, makes up roughly 25% of the total resistance. It handles that powerful high-current kick. Then, the holding coil, or TS coil, handles the remaining 75%. That provides the high resistance needed to safely restrict the current during the float phase. Now, you might be wondering, how fast does that accelerator coil actually do its job? Less than 100 milliseconds. I mean, literally less than the blink of an eye. In that fraction of a second, that low-resistance coil snaps the heavy armature plate open, and the rectifier, the brain of the whole operation, seamlessly switches over to the holding coil. It's an incredibly fast, highly efficient handoff. Moving on to Section 3, wiring the three-wire system, the rectifier brain. So, how does it orchestrate all of this? It does it using just 3 internal wires connected to the brake rectifier. Methodically, it breaks down like this. The red wire connects directly to the high-current accelerator coil. The blue wire connects to the low-current holding coil. And the white wire, that's your common center tap shared between the two of them. You absolutely have to memorize this. Understanding this specific color code is the key to diagnosing almost any fault in these systems. But here is a massive warning you really need to heed. While the 3-wire red, white, and blue logic remains exactly the same, the physical terminal numbers change depending on where your rectifier is actually mounted. If you have a BGE rectifier sitting in the motor's conduit box, you are typically landing those wires on terminals 1, 2, and 3. But if you are using a BMK rectifier mounted on a DIN rail in an electrical cabinet, those same brake coils connect to terminals 13, 14, and 15. You cannot guess this stuff. You must always check your specific wiring diagram. All right, Section 4, the catastrophes of miswiring, total destruction.
And when I say total destruction, I mean total mechanical and electrical destruction. Let's walk through these terrifying scenarios. Say you accidentally swap the red and blue wires. Well, the system sends its massive high-power kick right through the high-resistance holding coil. The magnetic pull is too weak, the brake completely fails to release, and the motor just blindly drives through the locked brake, turning that friction disc into actual ash. Yikes. What if you mix up the white common wire? Now you've bypassed the rectifier's internal switching entirely. It just continuously feeds high voltage into the low resistance coil, essentially turning it into a massive melting heating element until it dead shorts. And the worst one? If you bypass the rectifier entirely and apply direct, raw AC voltage, the alternating current causes the magnetic field to reverse rapidly. You get this incredibly violent mechanical chatter, followed by rapid, total coil destruction.
And why exactly does raw AC destroy it so fast? Because SCIW rectifiers are half-wave rectifiers. They convert AC to DC. And in that process, the DC output is actually 42% less than the AC line-in supply. So if you feed 480 volts of raw, unrectified AC directly into a DC coil that was only meant to receive a much, much lower voltage, yeah, it destroys the coil instantly. Game over.
Okay, let's take a breath. Section 5. Safe testing and diagnostics. Actionable rules.
So before you even think about installing a new module, you absolutely must test the existing coil. But remember, we are dealing with high voltage, and releasing a brake means a suspended load could literally fall on someone. So safety first. Step 1. Disconnect all supply power and mechanically lock out the load to make the area completely safe. Step 2. Unplug the red, white, and blue wires from the rectifier. Step 3. Set your digital multimeter to measure resistance in ohms.
So the crucial point here is comparing your multimeter readings to the logic we talked about earlier. Red to white should measure low resistance, right around that 25% mark. White to blue should measure high, about 75%. And measuring red to blue gives you the total resistance across the entire series. Now, if your math doesn't add up, or if you're seeing a dead short or an open line, well, the coil is destroyed. And here's the kicker. If the coil is damaged, you must replace the rectifier too. Why? Because a bad coil will instantly kill a brand new control module the second you power it up. Now, what if your resistance measures totally fine, but the brake is still overheating? That's when you do the quick diagnostic click test with the motor idle. If you command the brake to release and you hear a nice loud, sharp click, your electrical pull is working perfectly. Your heat is actually coming from mechanical friction like a dragging disc. But if you command it and hear a faint buzzing or just no click at all, the coil is failing to pull in, which points straight back to an electrical failure. All right, let's lock this all in with a quick fire round of do's and don'ts. Ready? Do always check coil resistance before installing a new module. Do ensure 1.5 to 2.0 millimeters of clearance on the manual release lever just so the brake can fully seat mechanically. Do mega test the coil to check for insulation breakdown against the ground. Okay, now for the don'ts. Don't adjust the air gap to 0. The magnetic field literally needs room to collapse. And absolutely under no circumstances, don't use the manual release lever to try and set brake torque. That is for manual emergency disengagement only.
So it all comes down to this. In a system where an entire facility's safety relies on a tiny split-second switch from a high current kick to a low current hold, before you apply power, are you absolutely sure you've measured the float? Respect the high voltage stakes, always follow the math, and never ever assume the wiring is correct. Thanks for joining this explainer, and seriously, stay safe out there.